Hi, and welcome back to the second part of topic 1.2. So this is quite a big topic, subtopic. So I thought it would be best to split it into two videos. So in the past slide in the last video, we looked at how to calculate empirical formula, like as a conceptually what it is and how it works, and how to get molecular formula if you know the empirical formula and the molar mass. Now we can also look at this example. So we could also be asked to calculate empirical formula from percentage composition. So this is a worked example where say that we have an organic compound that has 4.2% carbon, 6.95% hydrogen, and then 43.85% oxygen by mass. Calculate its empirical formula. So there are three steps to this. First would be to find the amount of each element in the compound. Amount being the amount in moles. Sorry, that's a bit messy. Amount meaning the amount in moles. So we can find the amount in moles by assuming. So we assume that we have 100 grams of the substance. Because if we have 100 grams of the substance, we can convert these percentages into masses, because 49.2% of 100 grams would just be 49.2 grams. And then we can also work out the molar mass of each of these, and then we can divide by that and then get the moles of each of these compounds, each of these elements in the compound. So that's what we have done, dividing the percentages, dividing them by the AR of each of the elements, and we have gotten 4.1 moles, 6.88 moles, 2.74 moles. We are next going to divide by the smallest number. So divide by the smallest number. The smallest number in this case was 2.74. So we're going to be dividing everything, all of these amounts, by 2.74, and then we're getting these numbers. So sometimes you might get really nice numbers, or it might be like 1.9 or 1.8999 or something like that, very close to the next number. So you could just round it up, probably. In this case, we've gotten something that is more like in the middle. So 1.5 is basically 3/2, and this is almost the same as 5/2. So we can't just round that up to 2 and 3 respectively. We have to cancel out the 2. And we can do that. So if the numbers are not whole, we can multiply by the denominator. So we can multiply everything by 2, as we have done here, and we get these numbers, and that is the empirical formula. So C3H5O2. All right, hope that makes sense. We could also calculate empirical formula from experimental data. So this question is saying that there's a magnesium ribbon reacted with oxygen by heating in a crucible to form magnesium oxide. So a crucible is, if you didn't know, is like this sort of stone bowl kind of thing, and it has like a lid. And so here, let's say we have our magnesium ribbon, and we are heating that. Say that this is our Bunsen burner. Right, so then they've given you certain values. They've given you the mass of the crucible and the lid on its own. They've given you the mass of magnesium and the crucible and the lid, and the mass of the contents, crucible, and lid after heating. Calculate the empirical formula. So the first step would be to calculate the mass of what you started with, magnesium. So if you subtract the mass of magnesium, the crucible, and the lid, 40.3, if you subtract that by 40.19, which is the mass of the crucible and lid on its own, we get 0.11, which is the mass of just the magnesium ribbon. Now, we are going to heat this with oxygen, and we're going to produce an oxide. So that contains oxygen. So the change in mass from 4.3 to 40.3 to 40.37 is due to the formation of an oxide, which is an oxygen. So we can find the mass of oxygen as well by doing 40.37 minus 40.3. So you've subtracted away the mass of the magnesium, crucible, and lid. The only thing left is the oxides, the oxygen component, which is 0.07. If we just divide each of these by their respective ARs, we will get their amounts in moles, which is the second step. And then finally, if we divide them all by the lowest number, which is by very little, 0.0044, we can get the ratio. So it's 1:1. So the empirical formula is actually MgO. It's actually common not to get a 1-to-1 ratio in this experiment because of various reasons, including impurities in the Mg. Other products could be produced, and there could be, if it's impure, maybe other things are reacting and stuff. And there could be a loss of product when conducting the experiment, if it's like lost to the environment, if the lid's not secure or something like that. Next, calculating empirical formula from a combustion analysis. In this question, this worked example, we're given that there is a organic compound composed of carbon, hydrogen, and oxygen. The complete combustion, that is menthol. That's the organic compound, and its complete combustion produces, the complete combustion of 0.1005 of menthol, grams of menthol produces this much CO2, this much H2O. Calculate the empirical formula. So what I do is I need to calculate the mass of carbon, hydrogen, and oxygen in each of these compounds. So I do this by multiplying the proportion of carbon in CO2 by the mass of CO2. So the AR of the AR of carbon is like roughly 12 or 12.01 to be precise, and the AR of oxygen is 16. So the molar mass of CO2 would be 12 plus 2 times 16. So that is over here. And the AR of carbon on its own is 12.01. So that is the proportion of carbon in this compound. If I multiply that by the mass of this compound, I should get the mass of carbon only in that in this molecule compound. We can do the same for hydrogen. So I'm multiplying 1.01, which is the AR of hydrogen. I'm multiplying that by 2 since there's 2 H's here, and divided by the molar mass of H2O, which is roughly 18.01. Multiply that by the mass of H2O, and we will get this, which is the mass of hydrogen only. Now, if we go back to the mass of menthol, we can subtract these masses from that, and we can get the mass of oxygen. That is the only other thing remaining in this compound because it's just carbon, hydrogen, and oxygen. Now, we can divide each of these by their molar masses. Their ARs to get these values. So that is the amount in moles. So we're converting grams into moles. Now, once again, divide by the smallest number, which is this. In that case, we get 10, 20, and 1. So that is the empirical formula, C10H20O. All right. Next, we are going to look at water of crystallization. So, water of crystallization is the fixed number of water molecules in one formula unit of a salt. So a salt could be something like NaCl, KCl, BaCl2, which is in this example over here, so on and so forth. Not just chlorides, but like many other things as well. Anyways, so experimental procedure to determine water crystallization. First, we measure the mass of the empty crucible and the lid. Next, add the mass of the known sample into the crucible, record the mass with the lid. Then heat the crucible for 5 minutes and hold the lid at an angle to allow gas to escape. Reweigh the crucible, lid, and the contents after cooling, and then repeat steps 3 and 4 in order to until the mass remains constant. So basically, we're ensuring that all the water has evaporated off and converted into steam, and we're left with only the fully dehydrated sample. So here's an example to determine the water of crystallization of the hydrated salt BaCl2 dot XH2O. So the dot shows that it is hydrated, and the X is the number of water molecules in the formula unit of BaCl2 of that salt. So we have the data. We have the mass of the crucible and the lid, the crucible, lid plus sample, crucible and lid plus sample after first heating and then after second heating. You will notice that after the first and second heating, there is no change, meaning that we have reached a point where all the water, or theoretically all the water, should have been evaporated off. So, first, we can find the mass of the hydrated sample by subtracting the mass of the crucible, lid, and sample, 26.5, by the mass of crucible and the lid, 21.5, which would give us 5 grams. Then we can find the mass of water. So the dehydrated sample, after removing all the water, after all the heating steps, is 25.76. So, and the mass of the hydrated sample with the crucible and the lid. So both of these have the crucible and the lid in the sample, so we don't have to subtract anything there to get the mass of sample after heating alone. So they will just cancel out. So we have 26.5 from here, the hydrated sample with the crucible and the lid, minus the dry sample, no water, plus crucible plus lid. That gives us 0.74, which is the mass of water. We can convert that into moles by taking 0.74 divided by the molar mass of water, which is roughly 18.01. Then we get this. The moles is 0.0411. We can then get the mass of the salt on its own. So this is water. The mass of salt on its own is 5, which is the hydrated salt, minus the water mass, which gives us 4.26. 4.26 divided by the molar mass of BaCl gives us 0.0205, and that is the moles of BaCl. And we can now that we have the moles of BaCl2 and the moles of water, we can find the ratio between them. So it's similar to kind of like empirical formula in that concept. And we can divide by the smallest number to get 2. So X should therefore be equal to 2. So yeah, that's how you would work through this sort of question. Assumptions made in this experiment: that all mass is lost due to water. All the water is driven off, and the crucible does not absorb any water, and that the salt does not decompose further. In a real-life setting, all of these might not hold true, but we make these assumptions to do these calculations. But if there is a discrepancy between this and like a reported value or a literature value, it could be accounted for by the fact that these assumptions might not be true. Right. This brings us to the end of topic 1.2. In the next video, we will look at topic 1.3. So I will see you then.